Final thing that we need to look at when it comes to simple harmonic motion is the idea of resonance. Now this is the classic example that is used. A bridge called the Tahoma Narrow Bridge in the 1950s was experiencing a huge wind blowing through the valley over which it was. And gradually over time it started to oscillate, and those oscillations increased in amplitude regularly. This that we're seeing here is an example of resonance, and we're going to look at exactly what causes that in this video. So every object that can oscillate with simple harmonic motion has something called a natural frequency. In fact, any system that can be caused to vibrate or oscillate has a natural frequency. And this natural frequency is the frequency at which a system will oscillate without a periodic force being applied to it. So in the example, a guitar string, when you pluck it, will oscillate at its natural frequency, and that frequency corresponds to the note that it will play. But we can apply a periodic force to an oscillating system, or a driving force, and see what effect that has. Here I have a little mass, and it's touched to a spring, which is attached here to a driver, where I can alternate the frequency. And at the moment, it's set below the natural frequency of this mass spring system. As I start to increase the frequency, you can see initially I have maximum displacement about there. I increase it to 0.89. My displacement, my amplitude, has increased to there. Bring it up to 0.94. I'm experiencing another increase in amplitude, until I get it to the natural frequency of the mass spring system, and I get an enormous maximum amplitude. So as my frequency was increasing towards the natural frequency of my mass spring system, my amplitude was increasing, peaking at the natural frequency. Once I've gone beyond the natural frequency, that amplitude will then start to drop off again. And this here, my amplitude frequency graph, is the typical kind of shape that you'd expect to see for any system that is being driven, that has a force forcing it to oscillate at a particular frequency. When it hits the natural frequency, the frequency at which it wants to vibrate, it will happily vibrate, and so you get the maximum amplitude. What you need to be able to do is explain, both in terms of amplitude and phase difference, what's happening as you approach the natural frequency, hit the natural frequency, and then drop past the natural frequency. So as you approach the natural frequency, as we saw in the video, the amplitude starts to increase. So approaching it, the amplitude increases, and the phase difference between the displacement and the periodic force also increases. The driver starts to lag ahead. When you hit the natural frequency, that's when you get your resonance, and that is when you are having the maximum amplitude of your oscillations. The important thing to remember about this here is that the phase difference between the displacement and the driver, that's our periodic force, becomes pi by 2 radians, or a quarter of a wavelength out of phase. Once you go beyond that natural frequency, because you're no longer driving it at the frequency at which it wants to be able to go, then the amplitude starts to drop off again. And now the phase difference increases from pi by 2 to pi radians. So approaching natural frequency, you have an increasing phase difference. Heading towards a phase difference of pi by 2 at the natural frequency, and increasing further towards pi radians after the natural frequency. I drew the graph earlier, but here's the actual graphs that we see. And you can see here we have had a look at what the effect of damping is. Now we know that damping will reduce the amplitude of an oscillation. Now if you've got a relatively small damping or very light damping effect, then your maximum amplitude is going to be very high. If you've got very heavy damping, okay, if your damping is much greater, then you're going to have a much smaller amplitude. But the key thing about this graph is that for greater damping, the amplitude is smaller at all frequencies. So if you're asked to compare or to suggest what the graph would look like, and you're starting off with this green smaller damping graph, and you're asked to say what the effect would be of increasing the damping in the system, well, not only will the maximum amplitude at the resonant frequency or natural frequency be greater, be less for the more damped system, but all of the frequencies leading up to and afterwards will yield a smaller amplitude for the more heavily damped system. And that's everything for SHM. Please feel free to go to revisedphysics.net to have a look at the fully worked practice questions and ask a question if you have any to ask.